Today I'm going to start covering the APChem Unit 6 content. This entire unit is over heat and thermochemistry. And so we're going to introduce some new topics to you, and these are going to build into some of the other topics that we hit in other units. So some essential questions about this unit is: why is energy released when liquid water becomes an ice cube? Why does your skin feel cold when water evaporates off of it? How does thermal energy transfer affect temperature, states of matter, and chemical bonds? Thermal, remember, means heat. How can energy changes be tracked and measured when energy can't be seen? And why do combustion reactions that form carbon dioxide always release energy? So these are some things that you guys should have seen in your first year chemistry. All these things are topics that we cover, and a lot of these are real life application. I know chemistry is all around us, but in these we constantly have things changing states of matter, and so a lot of this unit's going to talk about those different things, what makes it happen. So there's going to be some new terms. We have endothermic and exothermic processes. So when we're talking about the prefix endo, it means into, and then therm means heat. So it means that for endothermic, we are going to absorb heat. For exothermic, exo means out of, again, therm means heat. So for these, we are going to release heat. Heat energy is going to be represented when we start dealing with calculations. It's going to be represented by the letter Q, is how we're going to represent heat. The net energy change is called enthalpy. And this is a big word that we see all year long when we start talking about chemical reactions and heat, or just energy. It doesn't have to necessarily be heat. It could be just energy. It's represented by delta H. This symbol is referred to as naught, and it just means that they're measured under what we call standard conditions. And in AP Chem, you don't have to really learn any more in depth about that. It's just a set of numbers that we know exist. When we're talking about delta H, they've been measured by scientists and are considered to be a set of numbers based on the standard conditions. So let's talk about just changes in states of matter. There are 6 phase changes when we talk about changing between the 3 states of matter, solid, liquid, and gas. I want us to review what they are, and then we need to decide, is it exothermic or endothermic? So I'll start with one. So we can go ahead and say melting. And in melting, a substance is going to start as a solid, and it is going to change to a liquid. We see this in ice all the time. When we're trying to decide if it's endothermic or exothermic, there's a lot of ways that you can think about this. For right now, I'm going to tell us to think about it from the particle perspective. But as we advance through the school year, we're also going to get more in depth talking about those intermolecular forces between different substances. But for right now, we're going to talk about the states of matter. So this is going to go from a solid that has a very fixed set of particles to a liquid that is a little bit more free and move past each other. And if you want to think about in terms of water, we can think in the Fahrenheit or Celsius scale. Both of them, when they're frozen, it's either going to be at 0 degrees Celsius or 32 degrees Fahrenheit. For it to turn into a liquid, it's going to have to get a little bit warmer than that. So in order for it to go from a fixed solid to a freer flowing liquid, it is going to have to absorb energy. We have to change the position of these particles. We have to break intermolecular forces to be able to go from that solid to the liquid. So they're going to absorb, which means that melting is endothermic. Okay, the opposite of melting is freezing, which often will be called solidification. So the term freezing makes us think of ice. It makes us think cold. But there's a lot of substances that become a solid at a lot warmer temperature than water. And so sometimes it's called solidification. Freezing is fine. Just know that not everything is going to be at a cold temperature. For freezing, it is going to go from a liquid to a solid. And so when that happens, that means that it is going from something that has a little bit more energy, able to move around, free flow, to something that is in a fixed position. So in order for that to happen, I'm going to have to release energy, and it's going to be exothermic, because it's going to have to, particles are going to have to slow down, intermolecular forces are going to increase, they're going to become more attracted, and we release that energy out. Okay, those two are the first two of the 6 changes in state of matter. Let's go ahead and do 2 more. Another one that we could use is evaporation. Sometimes it is referred to as vaporization. Sometimes it is called boiling. In evaporation, it is going to go from a liquid to a gas. Again, we got to think about the particles. In order for us to go from a liquid to a gas, these particles are close to each other in a liquid. They can float, but they're going to be pretty close to each other. In a gas, they're going to be super spread out and be able to take up all kinds of space. If we think about like water, when it's a liquid, the particles can flow past each other. By the time they're gas, they're moving really fast. We're going to have to break intermolecular forces for it to go from a liquid to a gas. And so in all of these cases, to go from a liquid to a gas, I'm going to have to absorb energy, so it is going to be endothermic. The opposite of evaporation is condensation. It is going to go from a gas to a liquid, like we see whenever our mirrors fog up when we're taking a shower. Same thing, gas particles move fast, spread apart. They are going to have to slow down, come closer together for that to happen. It is going to have to give off energy, so it's going to be exothermic. Okay, and then our last 2 examples are the ones that are more commonly forgotten. They're the ones that are a little bit more obscure. And part of it is because we base everything we know about changes in state of matter based on water and how it does things. So water can go through what's called deposition. Deposition is where it goes straight from a gas to a solid. The opposite of deposition is sublimation. And at normal pressure and temperatures, water cannot go through sublimation. It's where it goes straight from a solid to a gas. Deposition would be like frost forming, but it doesn't work the other way very well. The pressure has to be very different. So for it to go from a gas to a solid, particles have got to slow down, get into a fixed position. They've got to create the intermolecular forces, because in a gas, they pretty much have no intermolecular forces because they're so spread apart. So for it to go to a gas to a solid, it's got to slow way down. It's going to be exothermic. It's got to give off energy to slow down from that gas to the solid. For it to go from the solid to gas, again, I've got to break all these intermolecular forces. I got to break up the attractive forces between the solid, get the particles to move around, spread really far apart, and so it is going to be endothermic. Those are our 6 phase changes. You need to be really familiar with those and easily be able to recognize what states of matter they start at and end at. System and surroundings, this is a big deal. When you're doing system and surroundings, the system is going to be the chemical reaction. Or it's not always a chemical reaction. It could be like the phase change. The surroundings are going to be everything else. So the surroundings would be the air. It could be the heat source, such as the air or like a stove or Bunsen burner. Beakers are considered to be like some sort of piece of equipment, could be surroundings. Thermometers are considered surroundings. All those things are surroundings. So the system is where it's actually happening, like where the chemical reaction or phase change is happening. Everything else is going to be considered the surroundings. When we talk about energy, we are going to talk about system and surroundings. You have to know where did it start at and where is it going. So when you're doing these problems, you need to really quickly identify what is the system and what is the surroundings. So when we're doing these problems, part of it that you need to be able to do is think about what's happening. So when we break a bond or an attractive force, so bonds would be like if I want to break sodium chloride completely apart, or attractive force would be like the attraction between water molecules. This is an endothermic reaction because it is going to have to take to break. On AP Classroom, it teaches us that TTB, takes to break. It takes to break any sort of bond or attractive force. If we're talking about particles, it takes to break to pull the attractive forces between the particles to be able to change into a new state of matter. So when we talk about this, since it takes that energy, since endothermic requires it, then our delta H that we talked about earlier is always a positive value because it requires that energy to be able to come into it. It requires the heat to be able to cause the reaction. These endothermic reactions are what we call energetically unfavorable. It doesn't really want to happen on its own. We have to do something to help it, and the products are typically less stable. In these reactions, your heat is going to flow from the surroundings to the system. So it's going to energy is going to come from outside of the system and flow into it. And we don't deal with a lot about work in AP chemistry, but work is done on the system. So like when we compress a gas or reduce the volume. The opposite is exothermic. This is a typo right here. This should be exothermic process because this one was an endothermic process. So when you form a bond or an attractive force, those intermolecular forces, then it's an exothermic because it frees to form. It frees energy. Energy is going to be released out whenever we are forming a bond or an attractive force. And so because of that, it frees energy. So it is going to release energy. So the enthalpy is going to be a negative number. Negatives and positive really matter in chemistry. They are important and they tell us a lot of information. Exothermic reactions are energetically favorable. They can happen without us having to do a whole lot, and the products are more stable. In an exothermic reaction, the heat is going to flow from the system to the surroundings. So the energy is going to actually start in the chemical reaction where the system is happening and go out into the surroundings. Or work is done by the system. So this would be an expansion of a gas to increase the volume. Let's read through this example and talk about it. So for a classroom demonstration, a chemistry teacher puts samples of two different pure solid powders in a beaker. The teacher places the beaker on a small wooden board with a wet surface, then stirs the contents of the beaker. After a short time, the students observe that the bottom of the beaker is frozen to the wood surface. The teacher asks the students to make a claim about the observation and to justify the claims. Which of the following is the best claim and justification based on the students' observations? So we have several options down below. We have two that are exo and two that are endo. So there's no way to eliminate something that's unreasonable. There's not a distractor necessarily on this one. So we have to think about what's happening. And so let's talk first about what happened to the water, okay? So we have to define our system and our surroundings. So our system is going to be these solid powders. These are going to be the system. The beaker is not even the system. It is just a container. So our system is going to be these solid powders that were combined. The beaker is surroundings. The small wooden board is surroundings. The already wet surface is the surroundings. All those things are surroundings. Okay. So our surroundings are going to be the beaker itself, the board, that wooden board, and the water that was just there. The water froze. So the students, that the beaker was frozen to the surface. For the water to freeze, that means that it went from a solid to a liquid. And that is going to be, it's going to have to go from sorry, I said that backwards. A liquid to a solid. I could write the right states of matter. So for it to be able to do that, it is going to go from those flowing particles to a more fixed, rigid position. It's going to be forming intermolecular forces depending on the substances. And so for it to go from the liquid to the solid, it is going to have to release energy because it's got to be able to slow these particles down to go to a solid. So that is an exothermic reaction. So this heat is still part of the surroundings. This heat has to go somewhere. This energy that's being released as the water froze, this heat has to go somewhere. So if we were talking about, I'm going to draw a really terrible picture. So we have our beaker with our powders in it. And we have this board. We have the water, and the water froze. Okay. When that froze, that energy is released. That is exothermic. That energy has to go somewhere. That is part of the surroundings. That means that in order for that to go somewhere, it is going to go into the system. It is being absorbed into the system. If it goes into the system, that is endothermic. These problems are really tricky because you have to think about surroundings and system. Because it would be so easy to be like, oh, water froze. But we're not talking about the water. The water happens to be there, but that's not what we're talking about. We're talking about these two powders. So it is not A or B because it is not exothermic. The freezing is exothermic, but that energy has to go somewhere from the surroundings into the system. The reason it happened is because in order for these two powders to be able to react with each other, they needed energy, and they pulled it away from the surroundings. They absorbed the energy from the surroundings. So it's going to be endothermic. It says endothermic physical change because the freezing of water is endothermic process. Well, that's not even true. Freezing is not an endothermic process, so that second part of this sentence is incorrect. It is going to be an endothermic chemical change because the temperature of the beaker and the water on the board decreased as the heat was absorbed by the chemical reaction. That is going to be your correct answer. These problems are pretty tricky, and you really have to think about, that's the reason I said it's so important to think about what is the system and what is the surroundings. When I run into these problems that have to do with just basic endothermic, exothermic, they're going to always try to trip you up. They're going to have words that are going to trip you up in these statements. And you have to be sure that you read an entire sentence, because once you figure out this was endothermic, if you just randomly pick C, it would have been wrong. If you had only looked at the fact that water was freezing, then you would have chosen A or B, which would have been wrong. Let's do one more. So it says, which of the following phase changes involves a transfer of heat from the surroundings to the system? Okay, so that's like our example that we had in the last one. So from the surroundings to the system. So that is going to be endothermic again. If we go back to our notes, endothermic, heat flows from surroundings to system. Exothermic, heat flows from the system to the surroundings. So we need to look at each of these and see what's happening and think about the phase change. So for it to go from a gas to a liquid, particles had to slow way down to be able to become a liquid. It's going to have to become more fixed position, more attractive forces. And so for it to slow down, it's going to end up having to give off energy. So it's going to be exothermic. So it can't be that one. This one goes from a gas to a solid, so it's going to have to slow way down to become a solid. That is also exothermic. Equally wrong. This one goes from a liquid to a solid, still has to slow down, and the attractive forces have to form. This is still exothermic because it frees to form, takes to break. This one is going to go from a liquid to gas. That means I had to speed the particles up. I'm having to break the attractive forces this time between the liquid and the gas so the particles can freely move. And so my correct answer is going to be D, because this one is endothermic, because the ammonia or NH3 molecules in the liquid phase must absorb energy in order to overcome their intermolecular attractions and become free gas molecules. So D is going to be our correct response. So on this topic, you really have to take your time and identify what the surroundings and system are and think about what that means for that problem.